Welcome, everyone. I'm just incredibly thrilled to have you joining us for a brand new deep dive today.
Yeah, it is great to be here.
We are taking a journey today that goes miles down.
Literally miles down into the Earth's crust.
Right, and we're examining a topic that, honestly, it completely reshaped my understanding of modern engineering and global supply chains, too.
It's one of those hidden pillars of the modern world.
Exactly. We are talking about molybdenum.
Chemical symbol Mo.
Mo, right. Sitting at number 42 on the periodic table.
Right there in group 6 as a transition metal.
And it boasts this exceptionally high melting point. It really is the unsung hero of the industrial world. Seriously, by the time we wrap up this discussion, you're going to look at the structural steel in buildings or the medical devices in hospitals.
Even the energy grids powering your city.
Yeah, you'll look at all of it in a completely different light.
It is a remarkable element. It's one of those foundational building blocks of infrastructure that operates almost entirely behind the scenes.
You rarely encounter it in its pure form, right?
Yeah. Almost never in your daily routine. But its presence as an alloying agent is absolutely critical. It provides the structural integrity, the thermal resistance,
The chemical stability.
yes, all of those things for the materials we rely on every single day.
So our mission today is to trace the entire life cycle of this metal. We really want to uncover exactly where molybdenum comes from.
Because a highly concentrated deposit of metal doesn't just, materialize out of the ether.
Right, it takes work, planetary work. We're going to examine the massive geological and tectonic forces that concentrate it deep underground,
As well as the highly interconnected global economy required to extract it.
and why its supply chain is critical to the future of global energy. To do this, we are pulling from a really robust stack of sources today.
The data we're looking at is fantastic.
It is. We're looking at a trio of highly detailed reports published by the U.S. Geological Survey.
The USGS.
Right. These include a specific deposit model for what geologists classify as arc-related porphyry molybdenum deposits.
Then there's another exhaustive report detailing the incredibly rare climax-type deposits.
And finally, a recent mineral commodities summary that breaks down the highly volatile modern global market.
The depth of the data in these USGS reports is exceptional. They synthesize decades of geological mapping.
Plus the complex geochemical and isotopic analysis.
Exactly. And economic forecasting. These models provide us with a highly technical roadmap to understand not just the physical characteristics of the deposits, but the deep-time planetary mechanics that govern how they form.
Okay, let's unpack this, because before we dive into lithospheric thinning and mantle wedge dynamics,
Which we will get to.
we absolutely will. But first, we need to establish the baseline of where you actually encounter molybdenum right now.
Its primary industrial claim to fame is its role in metallurgy.
Right. When metallurgists alloy just a relatively small percentage of molybdenum into steel, it completely alters the physical properties of that steel.
It drastically increases the material's strength.
Its toughness at high temperatures.
And critically, its resistance to corrosion.
So where does that end up? It is the key ingredient in the 300 series stainless steels.
Like the 316 grade.
Yeah, the stuff used in our water distribution networks and desalination plants.
It's utilized extensively in sterilized, corrosion-resistant surgical instruments, too.
And it is literally providing the high tensile strength required for the structural steel skeletons of modern skyscrapers.
And suspension bridges. The metallurgical mechanisms are quite elegant, actually.
How so?
Well, the molybdenum atoms help to stabilize the passive layer of chromium oxide that naturally forms on the surface of stainless steel.
Making the metal highly resistant to pitting corrosion.
Precisely. Particularly in environments rich in chlorides.
Like seawater.
Seawater, or areas where heavy de-icing salts are used on the roads.
And because of its exceptionally high melting point, 2,623 degrees Celsius?
That's right. And its ability to form highly stable hard carbides within the steel matrix, it's essentially irreplaceable in high-stress, high-temperature environments.
Jet engine turbine blades.
Nuclear reactor containment vessels, high-pressure industrial boilers.
It's everywhere. And the sources highlighted some incredible everyday applications that go way beyond just structural alloys.
Oh, the lubricant aspect?
Yes. Molybdenum is heavily utilized in elevator safety brake shoes.
But not as a structural metal there.
Right, it's not the brake itself. It's utilized as a highly specialized, high-load-bearing waterproof grease.
Molybdenum disulfide. Formulated as a dry lubricant, it's exceptionally slick under extreme pressure.
There's also this fascinating historical pedigree here that I loved reading about. Back in 1921, a metallurgist named C.H. Wills built a car.
The Will St. Clair.
Yes, the Wills St. Clair. It holds the distinction of being the first commercial automobile constructed extensively with molybdenum steel.
Which made it significantly lighter and stronger than its competitors at the time.
Furthermore, if you've ever noticed a highly vibrant, intense red-orange paint on a piece of industrial equipment,
Or specialized plastics.
yeah, there is a strong probability that pigment is derived from molybdenum orange.
Which is a complex lead chromate molybdate compound.
Its versatility across different chemical states is just staggering.
If we connect this to the bigger picture, it is crucial to understand that molybdenum does not exist as a free, uncombined metal in nature.
Right, you can't just stumble over a nugget of pure molybdenum in a stream.
You cannot simply walk up to an outcrop and extract it. In the Earth's crust, it is tightly bound in chemical coordination, most commonly with sulfur.
The primary ore mineral for this metal is molybdenite.
Molybdenum disulfide, or MoS2.
And from a mineralogical perspective, molybdenite is this soft, metallic gray mineral,
It actually has a distinctly greasy feel when handled.
which perfectly explains its utility as that elevator brake lubricant.
In fact, its crystalline structure is layered. You have strong bonds within the molecular sheets, but very weak van der Waals forces between the sheets.
So they slide easily over one another.
Exactly. This physical property is why early miners consistently misidentified it.
They thought it was something else entirely,
The name itself is derived from the Greek word molybdos.
meaning lead.
Right, because for centuries it was conflated with graphite or lead ores. It wasn't formally recognized as a distinct element until the Swedish chemist Carl Wilhelm Scheele isolated the oxide.
Back in 1778.
Yes. But moving from scattered atoms in the Earth's mantle to a concentrated, economically viable deposit of molybdenite
That requires tectonic and magmatic processes operating on a continental scale.
over millions of years.
That deep time formation is the core of our geological discussion today, but I want to ground this in the present first. We need to look at the economic reality of molybdenum.
The market dynamics are fascinating.
Currently, the industrialized world leans heavily on this metal, and the mechanics of how it actually enters the global market are surprisingly precarious.
Very precarious.
According to the data in the USGS mineral commodity summaries, the United States possesses robust domestic resources. We have an identified reserve base of approximately 5.4 million tons.
However, the global supply chain and the specific mining methodologies employed to extract it introduce massive volatility.
Global economics of molybdenum really present a unique case study in resource dependency.
This is a vital concept for anyone tracking global supply chains or critical minerals. A massive proportion of the global molybdenum supply.
Over 50%, right?
Well over 50%. And that figure holds true both domestically, within the U.S., and globally. That massive chunk is not the primary target of the mining operations that extract it.
It's a byproduct.
Yes. It is recovered as a byproduct, or in some cases a co-product, of copper mining.
This is such an important distinction for you listening. The infrastructure isn't built for the molybdenum.
The molybdenum is essentially a bonus.
You have these massive copper mines, primarily in the Andes or the American Southwest, and they just happen to have trace amounts of molybdenum locked in the exact same rock volume.
Precisely. The vast porphyry copper deposits of the world contain disseminated molybdenite.
Usually at very low concentrations compared to the copper sulfides.
But the extraction process is a marvel of chemical engineering. When these massive operations crush and mill hundreds of thousands of tons of rock per day,
Down to a fine powder.
they use a process called froth flotation to concentrate the metals,
They introduce the crushed rock slurry into massive tanks,
add specific chemical collectors, often xanthates, and bubble air through the mixture,
and the copper sulfide minerals attach to the air bubbles.
and float to the surface in a frothy concentrate.
However, molybdenite is naturally hydrophobic.
Due to that layered atomic structure we discussed, it also attaches to the bubbles and floats.
So the initial process just yields a bulk copper molybdenum concentrate. You haven't separated them yet.
Right. The mining operators then have to undertake a secondary, highly complex differential flotation circuit.
They typically add reagents like sodium hydrosulfide to depress the copper minerals,
Forcing the copper to sink while allowing the molybdenite to continue floating.
thereby separating the two.
But relying so heavily on this secondary separation process creates a glaring vulnerability in the market.
Because the global supply of molybdenum is effectively tethered to the economic health of the copper market.
It creates a classic inelasticity in the supply chain. If macroeconomic factors cause the global price of copper to decline,
Multinational mining conglomerates will naturally optimize their operations.
they may process lower volumes of ore, they might target higher-grade copper zones that just happen to have less molybdenum,
Or place entire copper mines on care and maintenance to preserve capital.
and when that copper production slows down, the output of byproduct molybdenum drops simultaneously.
And sharply. It's an unavoidable physical consequence of the geology and the processing circuitry.
Suddenly, the global market is faced with a supply deficit of a critical alloying metal.
But wait, the reports explicitly state that there are primary molybdenum mines in operation.
There are.
Facilities specifically designed and built, primarily in North America, to mine nothing but molybdenum.
Yes.
Why don't those primary producers just step in, turn on the tap, and fill the deficit when the copper byproduct dries up?
It comes down to the stark realities of mining economics and operational logistics. Primary molybdenum mines generally operate on a much higher cost curve than byproduct operations.
Because for a byproduct operation, the massive costs of drilling, blasting, hauling, and crushing are already subsidized by the copper revenue.
The molybdenum recovery is merely an incremental cost. Primary mines bear the entire capital and operational expenditure alone.
Oh, that makes sense.
Furthermore, heavy industry cannot simply toggle production like a light switch.
You can't just flip a breaker and suddenly mine 10,000 tons of rock.
Exactly. Ramping up a primary mine to meet sudden spikes in demand requires mobilizing heavy equipment, hiring specialized labor,
Often undertaking capital-intensive mill expansions. Bringing a mine off care and maintenance can take months.
or years. By the time a primary producer scales up to fill a supply gap, the market dynamics may have completely shifted again.
That perfectly explains the extreme price volatility we sometimes see. And looking at the global players listed in the USGS data really highlights the geopolitical distribution of this resource.
The major players are highly concentrated.
The dominant producers are China, Peru, Chile, the United States, and Mexico. Combined, those 5 nations account for over 90% of the world's molybdenum output.
But the critical detail in the data is the operational makeup of those nations.
Right. Of those 5 heavyweights, only the United States and China possess active production from both primary molybdenum mines and byproduct copper operations.
Peru, Chile, and Mexico are massive players, but their output is entirely reliant on byproduct recovery from their copper sectors.
Which means the national output of those 3 South American and North American nations regarding molybdenum is entirely captive to the base metal markets.
If you examine the U.S. import reliance data between 2020 and 2023, 64% of the molybdenum ores and concentrates imported into the United States originated from Peru,
Wow.
and another 12% came from Chile.
So despite possessing an estimated 5.4 million tons of domestic reserves, our supply chain for this critical mineral is heavily exposed to the operational stability, labor dynamics, and copper production metrics of the Andean mining sector.
It's highly interconnected.
Which begs the question for you listening. Why should this matter beyond the realm of commodity traders?
It matters because the global economy is currently undergoing a massive structural overhaul.
The transition toward clean energy generation, the modernization of aging electrical grids,
The expansion of geothermal power, the construction of next-generation nuclear reactors.
all of these initiatives demand unprecedented volumes of advanced, high-strength alloys. You cannot build a high-pressure, high-temperature geothermal pipeline or a durable offshore wind turbine tower with standard carbon steel.
They require the corrosion resistance and tensile strength that only molybdenum and similar alloying metals can provide.
If the supply chain for this metal becomes bottlenecked, the physical build-out of the clean energy transition faces severe delays.
It represents the unseen physical constraints of our technological ambitions. As developing nations industrialize and global infrastructure is forced to adapt to more extreme environmental conditions, the demand profiles for these materials are expanding rapidly.
Molybdenum is not a luxury commodity. It is a fundamental prerequisite for advanced structural engineering.
Absolutely.
That sets the stakes perfectly. We understand the demand, and we understand the fragile economics of the supply. Now, let's look at the Earth's manufacturing process.
The geology.
How does a planet concentrate enough of this highly dispersed element into a localized area that we can economically mine it?
Based on the USGS deposit models, there are 2 primary geological pathways that create world-class porphyry molybdenum deposits.
And they represent entirely different tectonic regimes. We have arc-related deposits, and we have climax-type deposits.
So the dichotomy between these two deposit types is one of the classic studies in economic geology.
Both systems yield massive volumes of disseminated molybdenite.
Yet the magmatic sources, the tectonic triggers, and the resulting chemical signatures are starkly different. Arc-related deposits are the more ubiquitous of the two.
As the name indicates, they are spatially and genetically associated with magmatic arcs.
The linear belts of volcanoes that form above subduction zones, you find these deposits distributed globally along active or ancient convergent plate margins.
The Western Cordillera of North and South America, the island arcs of the Western Pacific,
and complex collisional zones in Asia. Climax-type deposits, conversely, represent an extreme geological anomaly.
The geographic distribution of the climax-type deposits is just wild.
It really is.
The USGS reports detail that there are only 13 clearly defined, economically significant climax-type deposits known to exist on the entire planet.
And statistically defying all odds, every single one of those 13 deposits is located within a very specific corridor in Western North America.
They do not appear anywhere else in the global geologic record in the same concentrated high-grade form.
It is a profound anomaly that geologists have debated for decades. Why does the lithosphere beneath Western North America possess the exclusive magmatic recipe for these hyper-enriched systems?
Here's where it gets really interesting. Because to understand the anomaly of the climax deposits, we first must rigorously define the standard baseline.
We have to examine the arc-related systems to understand the baseline behavior of molybdenum in a subduction environment.
Let's do exactly that. Let's look at the arc-related deposits, which operate on what we can call the subduction engine.
The subduction engine is an apt descriptor. These deposits are the direct result of convergent plate tectonics.
For the massive deposits located in Western North America, such as those in British Columbia or Alaska, we are looking at the historical subduction of ancient oceanic plates.
Specifically the Farallon and Kula plates.
They were driven deep beneath the overriding North American continental plate during the Mesozoic and Cenozoic eras.
When that dense oceanic crust dives into the mantle, it's not just dry rock.
Right, it is dragging down millions of years of accumulated marine sediments, heavily hydrated minerals formed on the seafloor,
and trapped ocean water. As this massive slab descends hundreds of kilometers into the mantle, the temperature and pressure profiles increase exponentially.
And that increasing heat and pressure trigger a series of profound metamorphic reactions within the subducting slab.
Minerals like amphibole and lawsonite, which hold water in their crystal structures, undergo dehydration reactions.
They break down
and release massive volumes of aqueous fluids and volatile elements into the overlying wedge of extremely hot mantle rock.
These fluids act as a chemical flux. By introducing water into the mantle wedge, they drastically lower the melting temperature of the mantle rock.
The peritotite.
This induces partial melting, generating vast quantities of basaltic magma.
This fresh, buoyant magma then begins a long, complex ascent through the overriding continental crust.
But the magma that finally reaches the upper crust and forms these arc-related molybdenum deposits isn't the salt.
No, it is not.
The USGS reports are very specific about the chemistry here. By the time this magma stalls out a few kilometers below the surface, it has evolved
into calc-alkaline magmas, eventually cooling to form intrusive rocks like granodiorite, tonalite, or quartz monzonite.
The magma changes its identity completely on the way up.
The ascent through the continental crust is a transformative process. The initial basaltic melts derived from the mantle are immensely hot, often exceeding 1,200 degrees Celsius.
As they pool at the base of the crust or ascend through fractures, they physically melt and assimilate the surrounding older, silica-rich continental rocks.
Simultaneously, as the magma cools, higher temperature minerals like olivine and pyroxene begin to crystallize and settle out of the liquid.
A process known as fractional crystallization.
This combination of assimilation and fractional crystallization, often referred to as MSH zones.
Melting, assimilation, storage homogenization.
Exactly. This steadily enriches the remaining liquid magma in silica, water, and volatile elements, evolving it from a dark, iron-rich basalt into the lighter, silica-rich calc-alkaline magmas that host these deposits.
And within that chemical evolution, there is a specific isotopic and trace element signature that defines these arc magmas.
The models indicate that these systems are generally characterized by very low fluorine content.
Typically less than 0.1%.
They also exhibit low concentrations of elements like rubidium and niobium.
But moderate to high levels of strontium.
That specific trace element profile is the diagnostic fingerprint of a standard subduction-generated melt. The low rubidium and niobium, paired with the specific ratios of rare earth elements, confirm that the primary source of the melt was the fluid-fluxed mantle wedge, modified by standard crustal assimilation.
Crucially, this magma chemistry is fundamentally indistinguishable from the magmas that generate massive porphyry copper deposits.
They occupy the exact same tectonic real estate and derive from the same magmatic processes.
This is the crux of the geological detective story. If the source magmas for an arc-related molybdenum deposit and a porphyry copper deposit are essentially identical, what determines the final outcome?
Why do we end up with a mountain of copper in one location and a mountain of molybdenum in another?
Right.
The divergence between a copper system and a molybdenum system hinges on the microscopic behavior of elements during the crystallization of the magma chamber.
Governed by ionic radius and ionic charge.
Geochemists classify elements as either compatible or incompatible.
As a massive pluton of magma cools deep within the crust, silicate and sulfide minerals begin to form crystalline lattices.
Compatible elements are those whose size and charge allow them to easily substitute into the atomic structures of these early forming minerals.
They're systematically removed from the residual liquid melt early in the cooling history.
Incompatible elements, conversely, possess ionic radii that are too large or highly charged states that prevent them from fitting comfortably into standard silicate lattices.
Because molybdenum frequently exists in a highly charged state, like Mo4 plus or Mo6 plus GSE, it struggles to find a home in the early crystallizing minerals, like plagioclase, feldspar, or pyroxene.
It's essentially rejected by the forming rocks.
Precisely. Because it cannot easily integrate into the solidifying rock, molybdenum acts as a highly incompatible element.
It remains dissolved in the residual, steadily shrinking volume of liquid magma for as long as physically possible.
Copper, however, behaves somewhat differently.
While it can act incompatibly in certain conditions in these sulfur-rich arc magmas, copper frequently partitions into early forming sulfide minerals.
Or is incorporated into the structures of mafic silicates before the magma fully saturates with water.
So the key variable is the depth of emplacement.
The reports suggest that arc-related porphyry-molybdenum deposits generally form at greater depths in the crust than standard porphyry copper deposits.
Emplacement depth dictates the pressure regime, which in turn dictates the timing of volatile release.
Because the molybdenum-destined magma chamber is situated deeper, it is subjected to significantly higher lithostatic pressure.
The sheer weight of the overlying rock column.
This confining pressure prevents the dissolved water, chlorine, and sulfur gases within the magma from bubbling out or exsolving early in the cooling process.
The magma has to undergo extensive, prolonged crystallization before the vapor pressure of the residual fluids finally overcomes the confining pressure of the depth.
By the time this deep system finally reaches volatile saturation and a distinct superheated aqueous fluid phase separates from the silicate melt, a vast majority of the copper has already been locked away in early crystallizing phases deep in the pluton.
However, the incompatible molybdenum is still highly concentrated in the final remnants of the liquid melt.
When that late-stage fluid phase exsolves, it acts as an aggressive chemical scavenger,
stripping the abundant molybdenum out of the melt and concentrating it into the highly pressurized hydrothermal fluid.
Now we have an incredibly volatile scenario. It's like a giant pressure cooker.
Very much so.
We have a cooling, solidifying carapace of rock at the top of this magma chamber. And trapped immediately beneath it is a localized zone of superheated, highly pressurized, water-rich fluid.
That is absolutely saturated with scavenged molybdenum.
The pressure dynamics here are staggering. The fluid is expanding, the remaining magma is crystallizing and releasing more fluid, and the pressure on the surrounding rock is building continuously.
The mechanical forces eventually reach a critical failure point. The internal pressure of this metalliferous hydrothermal fluid steadily increases,
until it surpasses the sum of two resisting forces: the lithostatic pressure pushing down from above and the inherent tensile strength of the solid host rock encompassing the chamber roof.
And when that threshold is breached, the rock doesn't just crack.
Boom! It violently ruptures in a process called hydrofracturing.
It is an explosive subterranean mechanical failure. The solid rock of the chamber roof and the surrounding country rock shatters under the intense outward-directed fluid pressure.
In a geologic instant, an immense interconnected network of thousands upon thousands of microscopic to centimeter-scale fractures propagates through the rock volume.
The highly pressurized, molybdenum-rich hydrothermal fluids immediately decompress and rush into this newly generated fracture network.
As the fluids migrate away from the heat source and experience sudden depressurization, their solubility plummets.
The dissolved metals and silica rapidly precipitate out of the fluid, crystallizing primarily as quartz and molybdenite.
Effectively sealing the fractures they just created.
This repetitive cycle of pressure buildup, explosive hydrofracturing, fluid ingress, and mineral precipitation creates what geologists define as a stockwork.
If you examine an outcrop or a drill core from one of these deposits, the rock is heavily brecciated, thoroughly crisscrossed by a chaotic, multi-directional web of these mineralized quartz molybdenite veins.
Your rock is intimately permeated by the ore.
And the stockwork geometry dictates the fundamental mining metrics of these porphyry systems.
Because the hydrofracturing event shatters cubic kilometers of rock, the resulting mineral deposits are volumetrically massive.
The USGS reports categorize arc-related deposits as typically containing well over 50 million tons of ore,
with many significantly larger. However, because the molybdenite is dispersed throughout this vast network of tiny fractures rather than concentrated in massive solid veins, the overall grade of the deposit is exceptionally low.
We are looking at average grades ranging from a mere 0.03% to 0.22% molybdenum per ton of rock.
That low grade strictly dictates the engineering approach. You cannot selectively tunnel in and extract a 0.03% grade ore body.
These deposits demand bulk extraction methodologies. They are almost universally exploited via massive open-pit mining operations.
You have to systematically drill, blast, and excavate the entire mineralized mountain.
Haul millions of tons of rock to a concentrator, mill it down to the consistency of talcum powder, and rely on the froth flotation circuits we discussed earlier to recover that tiny fraction of a percent valuable metal.
A premier example highlighted in the data, which illustrates both the immense scale and the complex realities of resource development, is the Quartz Hill deposit located in southeastern Alaska.
It stands as the largest clearly defined arc-related porphyry molybdenum deposit discovered globally.
Extensive exploratory drilling has delineated an estimated resource of 1.6 billion tons of ore.
Yet, despite its staggering size, it remains entirely unmined.
It is situated within the boundaries of the Misty Fjords National Monument.
The profound environmental logistics of developing a billion-ton open-pit mine in a pristine wilderness, combined with the stringent permitting requirements and the historical volatility of molybdenum pricing, have kept it completely untouched.
It is a massive identified resource that is currently isolated from the global supply chain.
The Quartz Hill deposit is also geologically fascinating because the USGS notes that it presents somewhat of a transitional profile.
While its trace element chemistry and general characteristics place it firmly in the arc-related classification, structural studies indicate it likely formed around 27 million years ago during a period of localized post-orogenic extension.
Even though it is geographically situated within the footprint of an older, established subduction arc.
It displays certain hybrid features that begin to bridge the gap between our two primary models.
Geology rarely adheres to rigid binary classifications. There's always a spectrum. Systems like Quartz Hill demonstrate that as tectonic environments evolve from compression to extension, the magmatic plumbing systems adapt, producing deposits with overlapping characteristics.
But if Quartz Hill is blurring the line, the next category of deposits completely shatters it.
We are moving from the widespread low-grade subduction systems to the extreme anomalies of the geological world. Let's examine the highly concentrated, incredibly rare Climax-type deposits.
Climax-type deposits are the high-octane outliers of economic geology. If you want to see what occurs when magmatic evolution is pushed to its absolute chemical and thermal limits, you study the climax systems.
They defy the baseline rules established by the arc-related porphyries.
The first major divergence is the tectonic setting. We established that arc-related deposits require the subduction engine tectonic plates colliding and oceanic crust diving into the mantle.
Climax-type deposits do not form in compressive subduction zones.
They require the exact opposite tectonic regime. Climax-type deposits form in post-subduction, highly extensional environments.
This occurs when the regional tectonic forces shift from compression to tension. The continental lithosphere is literally being stretched, thinned, and pulled apart.
The archetypal example of this tectonic setting in North America is the Rio Grande Rift System and the broader Basin and Range province.
As the crust thins, it relieves the confining pressure on the underlying astenosphere, causing hot mantle material to upwell closely to the base of the continental crust.
This brings us to the source rock. Because the USGS reports are very clear that the magmas responsible for climax-type deposits do not originate from a fluid-flexed mantle wedge.
Instead, the intense heat from the upwelling mantle causes the base of the continental crust itself to undergo profound melting.
The protolith, the original rock that gets melted down, is typically composed of high-grade metasedimentary rocks or ancient granulites that reside at the deepest levels of the crust.
These melts create what are classified as A-type granites.
The designation A-type is critical here. It generally stands for anerogenic, indicating formation entirely independent of mountain-building collisions.
Though it can also denote alkaline or anhydrous compositions.
The key characteristic of these magmas is their extreme level of magmatic differentiation. They are generated by melting lower crustal rocks that have likely already been subjected to previous cycles of melting during older geologic events.
Therefore, the crustal rocks that finally melt to form the climax magmas are already highly specialized, heavily depleted in standard compatible elements, and immensely enriched in incompatible elements.
The USGS reports heavily cite the rigorous isotopic research conducted by geochemists like Stein and Hanna in the 1980s.
Their work analyzing the isotopic ratios of lead, sulfur, neodymium, and particularly the initial strontium-87 to strontium-86 ratios, provided the definitive smoking gun evidence.
That the magmas, the associated metals, and the sulfur in climax systems were derived almost exclusively from these ancient lower crustal sources.
With virtually zero input from the mantle.
So we have a highly evolved magma generated from the deep crust.
But the defining characteristic, the chemical anomaly that makes a climax-type deposit fundamentally different from anything else, is what the reports call the fluorine factor.
These A-type magmas are saturated with extreme concentrations of fluorine.
While our arc deposits contained less than 0.1% fluorine, climax-type magmas routinely exhibit bulk fluorine concentrations exceeding 1%, sometimes significantly higher.
They're also heavily enriched in those incompatible elements we discussed earlier, particularly rubidium, niobium, and tin.
What's fascinating here is exactly what fluorine does to the magma. It completely changes the physical properties of the melt.
Fluorine is a highly reactive, strongly electronegative halogen. When it is dissolved into a granitic magma in high concentrations, it actively attacks and breaks the strong silicon-oxygen-silicon bonds that form the polymerized tetrahedral network of the melt.
By depolymerizing the magma, fluorine completely rewrites the cooling behavior of the system. Its most significant impact is a dramatic depression of the solidus.
We need to define the solidus clearly, as it is central to why these deposits are so rich.
In igneous petrology, the solidus is the specific temperature threshold at which a given volume of rock completely solidifies into solid crystal, or conversely, the temperature at which melting first initiates.
A standard granitic magma, like those in the arc systems, might reach its solidus and freeze solid at temperatures around 700 to 750 degrees Celsius.
However, extreme fluorine enrichment depresses that solidus significantly.
A highly fluorinated climax-type magma can remain as a mobile liquid melt at temperatures well below 600 degrees Celsius, perhaps even down to 500 degrees.
Which means the magma chamber remains slushy and active for a vastly extended period of geologic time.
Exactly. This extended liquid lifespan permits extreme, protracted fractional crystallization. The magma continues to slowly crystallize standard minerals, progressively enriching the remaining, steadily shrinking liquid volume with ever higher concentrations of highly incompatible elements like molybdenum.
Without the entire system freezing prematurely.
Furthermore, the depolymerization caused by the fluorine drastically reduces the viscosity of the magma. It transforms from a thick, sluggish paste into a highly fluid, highly mobile melt.
This low viscosity allows the magma to ascend rapidly through deep crustal faults.
But the extreme concentration of fluorine triggers an even more bizarre chemical phenomenon as the magma nears the surface.
The reports indicate that when the fluorine and water concentrations reach a critical threshold, the system undergoes liquid immiscibility.
Liquid immiscibility in a silicate melt is a highly complex physical chemistry process. As the magma crystallizes and forces the halogens and water into the remaining liquid, the melt eventually unmixes.
It separates into two distinct, coexisting liquid phases that cannot blend, much like oil and water separating in a beaker.
One phase is a denser, silica-rich silicate melt. The second phase is a highly mobile, low-density, aqueous saline fluid that is exceptionally rich in fluorine, chlorine, and alkali metals.
This immiscible fluid phase is an incredibly aggressive chemical solvent. It sweeps through the remaining silicate melt, highly efficiently scavenging the hyperconcentrated molybdenum and transporting it.
Because this fluid phase is so light and buoyant, and the surrounding magma is so remarkably fluid due to the low viscosity, this metalliferous fluid races to the very top of the magmatic column.
The USGS reports describe the geometry of these intrusions as cupola-like.
A cupola is an architectural term for a small dome. In geology, it refers to an inverted teacup or a highly localized finger-like projection at the very apex of the larger, deeper magma chamber.
The fluorine molybdenum-rich fluids aggressively pool at the very top of this cupola.
The structural geology here is defined by extreme concentration. The entire volatile budget and metal inventory of a massive, deep-seated batholith are forcefully channeled and focused into a very small structural volume at the apex of the cupola.
As the pressure inevitably builds in this localized zone, the system experiences the same hydrofracturing mechanics we saw in the Arc deposits.
However, because the fluid was chemically segregated and hyperconcentrated by the fluorine dynamics, the resulting ore precipitation is spectacular.
The entire sequence of fluid exsolution, explosive fracturing, rapid cooling, and dense molybdenite precipitation frequently occurs within a highly restricted vertical span of just a few hundred meters around the apex of the stock.
The hyperconcentration directly translates to the economic metrics of the deposit. While ARC deposits hover around 0.03% molybdenum, the ore grades in climax-type systems are substantially higher,
Frequently ranging from 0.1% to over 0.3% molybdenum.
in the realm of bulk tonnage mining, a tenfold increase in grade is economically massive.
And despite being localized in these cupolas, the sheer volume of metal mobilized makes these deposits huge, containing anywhere from 100 to over 1,000 million tons of high-grade ore.
But the deep-seated nature of these cupolas, often situated hundreds or thousands of feet beneath the current topography, presents significant engineering challenges.
They are rarely amenable to conventional open-pit excavation. To access these deep, massive ore bodies, mining engineers frequently deploy a highly specialized, capital-intensive underground extraction method known as block caving.
The Henderson Mine in Colorado, one of the premier climax-type deposits, is a global benchmark for this specific engineering technique.
The mechanics of block caving are an engineering marvel. Instead of starting at the surface and digging down, the miners sink deep shafts and drive horizontal tunnels called drifts completely underneath the massive ore body.
They establish an undercut level directly below the ore.
They meticulously drill and blast a massive horizontal void across the entire footprint of the deposit, effectively pulling the foundational support out from under millions of tons of solid rock.
It is the deliberate, highly controlled induction of a massive structural failure.
Once the undercut is blasted, gravity becomes the primary mining tool.
The immense block of overlying fractured ore rock loses its support and slowly begins to cave in on itself.
As the rock mass subsides, the internal stresses and the friction of the collapse cause the rock to naturally fragment and crush itself into manageable pieces.
This fragmented ore continuously funnels down through pre-engineered extraction bells into the extraction level below, where automated loaders scoop the rock and transport it to underground crushers before hoisting it to the surface.
It is the most cost-effective method for extracting massive, low-grade underground deposits, but it requires profound geotechnical modeling to ensure the cave propagates predictably and does not compromise the stability of the entire mining operation.
So what does this all mean? We have thoroughly mapped the two disparate geological pathways that yield the molybdenum our modern infrastructure demands.
We have the widespread low-grade subduction-driven arc systems and the ultra-rare high-grade, high-fluorine extensional climax systems.
But this necessitates a critical pivot in our discussion.
We know why we need the metal. We know the immense cumuluses the Earth utilizes to concentrate it, and we know the heavy engineering required to extract it. Let's move to the ultimate consequence. What are the environmental realities?
When industrial mining operations excavate these massive mountain-scale geological systems, crush the rock, and expose millions of tons of unweathered minerals to atmospheric oxygen and surface water, what is the ecological cost?
The environmental footprint of a mining operation is not arbitrary. It is rigidly dictated by the fundamental mineralogy and geochemistry of the specific deposit type.
The chemical reactions that occur when ore and waste rock interact with the hydrosphere are direct consequences of the deep-time magmatic processes we just examined.
Therefore, the environmental liabilities of an arc-related deposit differ markedly from those of a climax-type deposit.
Let's analyze the environmental profile of the arc-related deposits first.
The findings in the USGS reports present a somewhat counterintuitive conclusion. Despite the staggering physical scale of these open-pit operations moving hundreds of thousands of tons of rock daily arc-related porphyry molybdenum deposits, are generally classified as having relatively low geo-environmental hazard potentials compared to many other types of base metal mines.
The mitigating factor in arc-related systems is the overall volume and specific composition of the sulfide mineralogy. It is crucial to remember that molybdenite itself is a sulfide.
MOS2. However, the severe environmental issues at many mining sites, such as massive copper or lead-zinc operations, stem from the high concentrations of associated gangue sulfides, overwhelmingly iron sulfide, universally known as pyrite.
When pyrite is excavated and exposed to atmospheric oxygen and water, it oxidizes through a complex biologically mediated chemical reaction. This oxidation process generates significant volumes of sulfuric acid and dissolved iron.
This is the fundamental mechanism behind acid mine drainage, which is arguably the most pervasive and destructive environmental legacy of hard rock mining.
But the data indicates that arc-related molybdenum deposits naturally contain relatively low volumes of pyrite, generally constituting less than 5% of the rock mass by volume.
Precisely. The initial acid-generating potential of the waste rock is fundamentally constrained by the lack of fuel for the reaction, but the environment benefits from a second, highly effective natural defense mechanism.
The late-stage hydrothermal fluids that circulate through these arc deposits during their formation typically precipitate extensive networks of veins containing carbonate minerals, primarily calcite, which is calcium carbonate.
In the context of waste rock weathering, calcite functions as a powerful, naturally occurring antacid buffer. As the minor amounts of pyrite oxidize and generate small localized amounts of sulfuric acid, the pervasive calcite reacts with the hydrogen ions, effectively neutralizing the acid on contact.
Consequently, the effluent waters draining from the open pits and the massive waste rock repositories of arc-related operations typically maintain a near-neutral pH balance.
The reports included a remarkable field study that powerfully illustrates this benign chemistry. At the Endako line, located in British Columbia, a classic, massive, arc-related open-pit operation researchers deliberately released populations of trout into a flooded, decommissioned open-pit lake on the mine site.
The water within this pit lake exhibited elevated concentrations of dissolved molybdenum resulting from the submerged rock walls, averaging around 33 milligrams per liter.
For context, the natural background concentration of molybdenum in pristine freshwater is typically around 1 microgram per liter.
Despite being exposed to molybdenum levels tens of thousands of times higher than baseline, the trout inhabited the pit lake for 14 months and exhibited no signs of chronic toxicity, reproductive failure, or mortality.
It strongly suggests that when maintained in a neutral pH aquatic environment, dissolved molybdate anions are surprisingly inert and pose minimal threat to aquatic vertebrate life.
However, while the acute chemical toxicity of the drainage may be low, it is imperative that we do not conflate chemical neutrality with zero environmental impact.
The physical footprint of arc-related extraction is staggering. Because the average grade is roughly 0.05%, the waste-to-ore ratio is often near 1:1 or higher.
To process the ore, it must be ground to micrometer-scale particles, creating vast volumes of silty tailings that must be permanently stored behind massive engineered dams.
The sheer scale of the land disturbance, the diversion of local watersheds, the destruction of surface habitat, and the perpetual geotechnical management required to ensure the long-term physical stability of these massive tailings impoundments represent profound ecological disruptions.
That physical reality is undeniable, but when we transition to analyzing the environmental footprint of the climax-type deposits, the severity of the hazard profile escalates dramatically.
The USGS sources draw a stark contrast here. The climax-type deposits are categorized as presenting significantly higher, more aggressive environmental risks.
The paradox of the climax deposits is that the exact same unique magmatic chemistry, the extreme fluorine enrichment, and the intensely localized volatile concentration that created such high-grade, economically desirable ore bodies also engineered highly reactive, chemically volatile rocks.
The primary culprit is the specific style of hydrothermal alteration that surrounds the deposit. As the superheated, highly acidic magmatic fluids permeate outward from the cupola, they aggressively bake and chemically alter the surrounding host rock.
The most problematic zone is defined by quartz-sericite pyrite alteration, universally abbreviated as QSP.
So, unlike the arc systems we just discussed, These climax systems generate a massive halo of rock, heavily impregnated with pyrite.
Yes. The pyrite concentrations in QSP altered zones are substantial. Compounding the issue, the intense acidic nature of the original hydrothermal fluids completely leached away or destroyed any naturally neutralizing carbonate minerals like calcite.
The rock is stripped of its buffering capacity. When these QSP-altered rocks are fragmented during mining and piled into expansive waste dumps, they weather and break down exceptionally rapidly upon exposure to oxygen and precipitation.
The abundant pyrite oxidizes unchecked, generating aggressively highly acidic drainage waters, often with pH values dropping below 3 or even 2.
But the hazard extends far beyond the acidity itself. This low pH fluid acts as a powerful solvent. As it percolates through the waste rock, it attacks and dissolves the silicate gangue minerals, liberating massive concentrations of heavy metals directly into the water column.
The data details that we are looking at drainage waters loaded with hundreds, sometimes over 1,000 milligrams per liter of dissolved sulfate, aluminum, manganese, and iron.
And because this is a climax-type system, the signature anomaly of the deposit, the fluorine factor, returns as a major environmental liability.
The extreme magmatic fluorine budget is locked within the minerals of the altered rock, particularly within the sericite micas and fluorite veins.
The aggressive acidic weathering process attacks these minerals, releasing hazardous concentrations of dissolved fluorine directly into the surface and groundwater systems.
The reports specifically note that these highly acidic, multi-metal, and fluorine-laden waters pose severe, immediate threats to downstream aquatic ecosystems, riparian habitats, and potential drinking water aquifers if the drainage is not meticulously captured, contained, and subjected to highly expensive, perpetual active water treatment facilities.
The rapid weathering of the QSP rock also compromises physical stability. In natural erosional scars near the complex Cresta mine in New Mexico, the pervasive, rapid chemical breakdown of the highly altered rock drastically weakens the slopes, frequently triggering massive, destructive debris flows and landslides during heavy precipitation events.
The environmental complexities extend beyond water chemistry and slope stability. They infiltrate the biological food web in ways that resemble a complex biochemical thriller.
Now, the pure molybdenite mineral itself, NaOS2, is highly insoluble. If you were to ingest a chunk of molybdenite, it would pass through your system largely unreacted. It is essentially non-toxic in its sulfide form.
However, the weathering of these deposits, particularly in environments with naturally alkaline soils, or in scenarios where mining waste rock has been heavily treated with lime to artificially neutralize the acid drainage, fundamentally alters the chemistry.
Under these specific, higher pH conditions, the molybdenum oxidizes and becomes highly mobile and highly soluble as the molybdate anion.
This mobilized, soluble molybdate is readily and aggressively absorbed by local vegetation through their root systems. The plants themselves are remarkably resilient to the metal.
They can actively accumulate astonishingly high concentrations of molybdenum in their tissues without exhibiting any significant signs of phytotoxicity or stunted growth. They act as passive bioaccumulators.
The critical environmental danger only emerges when we move higher up the trophic levels of the food chain, specifically impacting ruminant animals. This includes domesticated livestock, such as cattle and sheep, as well as wild unguidates like moose or elk that forage in these environments.
This specific biological pathway, detailed in the research, is utterly fascinating. A grazing animal, like a moose, consumes massive quantities of this local vegetation that is invisibly loaded with accumulated molybdenum. What exactly occurs when that plant matter reaches their digestive tract?
Ruminant biology relies on a highly specialized, multi-chambered stomach system. The primary chamber, the rumen, operates as a massive fermentation vat, densely populated by specialized microflora, notably sulfur-reducing bacteria.
When the molybdenum-rich plant tissue enters the rumen, it is subjected to this unique chemical environment. The dissolved molybdate reacts directly with the hydrogen sulfide gas produced by the bacteria during the fermentation of dietary sulfur.
This specific reaction synthesizes complex, highly reactive molecules known as thiomolybdates. These thiomolybdate complexes possess an intense, almost magnetic chemical affinity for copper ions.
Which brings us back, full circle, to copper, but this time functioning within a biochemical context rather than an economic one?
Exactly. Copper is an absolutely essential trace nutrient required for a myriad of metabolic functions, enzyme synthesis, and neurological health in these animals.
However, as the thiomolybdates form in the rumen and enter the bloodstream, they bind fiercely to the available copper within the animal's body. They lock the copper into insoluble complexes, rendering it completely biologically unavailable for cellular use.
They effectively strip the crucial copper out of the animal's metabolic system. This induces a severe, rapid-onset copper deficiency, a well-documented toxicological condition known as molybdenosis.
If left unmanaged, molybdenosis results in severe chronic diarrhea, stunted growth, extreme emaciation, severe anemia, depigmentation of hair, severe neurological degradation, and ultimately high mortality rates within the affected herds or local wildlife populations.
The interconnectedness of these systems is staggering. The microscopic ionic charge of a cooling magma chamber millions of years ago dictates the eventual fluorine concentration and alteration mineralogy of the rock.
That mineralogy dictates the precise pH and chemistry of the groundwater when exposed by mining. That water chemistry dictates the solubility and uptake of the metal into the local flora.
And finally, that bioaccumulated metal reacts with the specific sulfur-reducing bacterial colonies in the stomach of a grazing moose to induce a lethal copper deficiency. It is a profound demonstration of the butterfly effect, driven entirely by heavy metal geochemistry.
Which brings us to a point requiring rigorous, critical analysis from anyone engaged in discussions concerning energy policy or infrastructure development. As modern society aggressively demands ever-increasing volumes of these specialized critical metals, as we legally mandate sweeping global infrastructure overhauls and aggressively transition entire power grids toward clean, green energy technologies, we are forced to confront the harsh physical realities of extraction.
The vital necessity of molybdenum to manufacture the corrosion-resistant alloys required for offshore wind turbines, advanced nuclear reactors, and high-capacity electrical transmission lines is scientifically undeniable.
However, we must continuously and soberly weigh that technological necessity against the rigorous, highly expensive, and often perpetual environmental management required to safely extract it. This is especially critical when evaluating the development of the highly reactive, chemically volatile climax-type sources.
There is no frictionless path in the energy transition. Every clean technology, every advanced alloy originates in an open pit or an underground mine, and every mine exacts an ecological toll that must be engineered, mitigated, and managed over centuries.
And that profound reality brings us perfectly to the conclusion of our deep dive today. We have traced the incredible hidden life cycle of molybdenum. We started deep within the mantle subduction zones, watching oceanic plates dehydrate to fuel the massive, low-grade arc systems that provide the bulk of our current supply.
We analyzed the extreme physics of the stretching continental crust over the Rio Grande Rift, where extreme fluorine enrichment completely rewrites the rules of silicate melts, generating the ultra-rare, high-grade climax deposits.
We unpacked the precise atomic behaviors, like ionic radius, that dictate why copper and molybdenum part ways deep in the crust. And we've seen the complex economic web that ties the fate of this critical metal almost entirely to the volatile fluctuations of the global copper market.
My ultimate takeaway for you listening to this is to embrace a new perspective. The next time you utilize a piece of sterilized stainless steel medical equipment, or rely on the structural integrity of a suspension bridge, or even recognize the bright pigment in an industrial coating, pause for a moment.
Recognize the unimaginable geologic violence, the millions of years of deep-time chemical fractionation, and the incredibly complex, globally interconnected human engineering required to pull that specific atom of molybdenum out of the dark rock and integrate it into the infrastructure of your daily life.
It is a remarkable element that operates invisibly to sustain modern engineering. Understanding its origins and its vulnerabilities provides us with a significantly deeper appreciation for the profound complexities of our planet's geology and the fragility of our industrial supply chains. And as a final provocative thought for you to consider, we extensively discussed how the global market currently relies heavily on the byproduct recovery from massive copper mining operations to meet the world's molybdenum demands. We are essentially coasting on the massive outputs of the Andean and North American copper sectors.
However, careful analysis of the long-term USGS forecasting data reveals a looming structural deficit. Several of the largest, most productive world-class porphyry copper mines currently in operation are projected to reach the absolute end of their geological and economic lifespans by the mid-2030s. Their ore grades are steadily declining, the pits are reaching their maximum economic depth, and they will simply exhaust their viable reserves.
So we are facing a scenario where the primary source, the massive copper byproduct taps, will inevitably begin to dry up within the next decade.
It is a demographic certainty of the mining cycle. I leave you to ponder the implications of this convergence. When those massive byproduct operations begin to shutter their mills, right at the exact moment when the global clean energy transition reaches its peak, demanding unprecedented volumes of molybdenum to deploy the next generation of green infrastructure. How will the global economic machinery adapt?
Will the sheer force of demand compel the industry to aggressively permit and develop massive, environmentally complex primary mines, like the highly volatile climax types, to fill the supply void? Or will a critical bottleneck in the supply of this unsung alloying metal critically stall our global infrastructure ambitions before they can be fully realized?
That is a deeply complex, highly consequential challenge. We absolutely require the advanced metallurgy to build the technologies that will mitigate climate change, yet extracting that metal inherently impacts the local environment we are trying to protect. It is one of the definitive engineering and policy puzzles of the 21st century. Well, that concludes our time for today. Thank you so much for joining us on this extensive journey deep into the Earth's crust.
The pleasure was mine. Thank you for listening, and continue to rigorously question the systems and materials that build the world around you.
We will see you on the next deep dive.